Hello, I am Professor Narendra Kumar Pandey from University of Lucknow Physics Department. And today I am here before you with my 14th lecture of the laser lecture series. And today's topic is modes of a confocal resonator system. तो आप सबका आज के इस 14वें लेक्चर में स्वागत है जिसका कि टॉपिक है modes of a confocal resonator system. Now here we have a confocal resonator system. The radius of curvature of either of the two mirrors is r, and the separation between the two mirrors is also r. So we have a confocal resonator system. So consider a confocal resonator cavity consisting of a pair of mirrors, each of radius of curvature r and separated by a distance r from each other. Now, a mode of the cavity will be a field distribution which is such that after one complete round trip through the resonator, the resultant field distribution is the same as the distribution we had started with. So, for example, if we have any such field distribution at any point, let us suppose, then it goes from here to this, it goes from here after reflection to this and comes back to the same. So if the initial field distribution and the final field distribution both are the same, then this field distribution will represent a mode of oscillation of the cavity resonator. Now, this confocal cavity is symmetric about the midplane n dash. You can see this is symmetric about the midplane n dash. This is n dash. The modes can be obtained from the condition that the field distribution across the plane A dash, that this is A dash and this is B dash, this is M1, this is M2. So the cavity is symmetric about the midplane n dash. The modes can be obtained from the condition that the field distribution across the plane A dash must be the same as that across the plane B dash, which is obtained after one half round trip. So allowed frequencies of oscillation will be only those for which the phase change after one half round trip is an integral multiple of pi. Had it been one full round trip, it would have been an integral multiple of 2 pi. It is half round trip, so it must be an integral multiple of pi. A given field in the plane A dash propagating to the right first diffracts over a distance r and then suffers a reflection at mirror M2 to complete one half round trip. That we have very easily seen. Any beam that first goes from here to this place will be reflected back from here. So traveling of this distance and coming back from after reflection from this one is half round trip. We can say that. So a field in the given plane A dash propagating to the right first diffracts over a distance r and then suffers a reflection at mirror M2 to complete one half round trip. The effect of diffraction was given by expression 9 in the last lecture, and I will quote that from there. Gxyz is equal to I by lambda z e to the power of minus I kz double integral fx dash y dash 0 exponential minus ik by twice z x minus x dash whole square plus y minus y dash whole square dx dash dy dash. And of course, the effect of reflection also on the phase distribution was given by the formula there, by the expression number 13, and that if I quote, then it was Pm is equal to exponential ik by r x square plus y square. So this 13 and 14 expressions we have already seen in the last lecture, that is number 13. So modes of the resonator. We have expression 13 and expression 14. So let us consider 13 and 14 and let fxy represent the field on the plane A dash. Let fxy represent the field on the plane A dash, and you know which one is A dash? I'm talking about this one. So here we have field fxy. So let fxy represent the field on the plane A dash. This field gets diffracted in going from mirror M1 to M2, and we get the following resulting expression that we have already quoted in the last expression, that is 14. This expression we get because of that. Here, R is the distance between the mirrors. The integral is carried out over the area of the mirror. The field on the plane BB dash after 1/2 round trip. Now, naturally, this is GXY, and this is the effect of reflection from the second mirror. So, the field on the plane BB dash after 1/2 round trip will be given by HXY is equal to GXY into exponential IK by RX square plus Y square, and that was given by expression 13. You can see at the bottom here that we had seen in the last lecture. So we have Hxy is equal to Gxy exponential Ik by Rx square plus Y square. If the field distribution Fxy represents a mode, let us say if the field distribution Fxy represents a mode, then naturally Hxy should be equal to sigma Fxy. If naturally Fxy represents a mode, then Hxy is equal to sigma Fxy, where sigma is a complex constant. The magnitude of sigma will determine the losses suffered by the field, whereas the phase of sigma will determine the phase shift in 1/2 round trip. There will be two factors in sigma. That is, the magnitude of sigma will determine the losses suffered by the field, whereas the phase of sigma will determine the phase shift in 1/2 round trip. So put equations 16 and 17 in 15. We have 16 and 17. And if we put that back into 15, then what we are getting? Sigma Fxy is equal to I by lambda r exponential, because Z is equal to R here. So I by lambda r exponential minus Ik Z, it was there. So it is exponential minus Ik R. So sigma Fxy is equal to I by lambda r exponential minus Ik R, double integral over the aperture dx dash dy dash fx dash y dash exponential minus Ik by twice R, x dash square if we have expanded plus y dash square minus 2x x dash minus 2y y dash into exponential Ik by twice R x square plus y square. This is what we are getting as sigma Fxy when we put 16 and 17 in equation 15. Now let us introduce a new function, and that is Sxy is equal to Fxy into exponential Ik by 2R x square plus y square. So Sxy is a new function we have introduced, which is equal to Fxy exponential minus Ik by twice R x square plus y square. Let us now introduce the following set of dimensionless variables. We introduce the following set of dimensionless variables, and they are xi is equal to square root of k by r into x, and eta is equal to square root of k by r into y. These are the two dimensionless variables, that is xi and eta, that we are introducing here at this stage. So use equation 19 and 20, that is Sxy is equal to Fxy. We are using this expression and this expression. In expression 18, we put it over here. So what we get? We have sigma in place of Fxy. You can see from here we have Sxy is equal to Fxy exponential minus Ik by twice r x square plus y square. And from here, we write things like sigma Sx, sigma S xi eta. So use 19 and 20 and 18 and get sigma S xi eta is equal to I by twice pi e to the power of minus IKR in double integral over the aperture a dash S xi dash eta dash exponential I xi xi dash plus eta eta dash and integrated over d xi dash d eta dash. This is expression 21. Now here the integration is taken over the modified limits of integration, because we have introduced xi and eta as two new dimensionless variables. So integration will be carried over the modified limits of integration that will come in view of the changed variables xi and eta, which you can see here, d xi dash d eta dash in place of dx dash and dy dash. Now, to simplify the analysis, we assume the mirrors to have a rectangular cross-section with dimensions 2a and 2b. Rectangular cross-section we have assumed, and dimensions are 2a and 2b. Thus, equation 21 that we have just written, thus equation 21 may be written like sigma S xi eta is equal to I by twice pi exponential minus IKR. Now the limits are changed from minus xi naught to plus xi naught. minus eta naught to plus eta naught s xi dash eta dash exponential I xi dash plus eta dash and integrated over xi dash and eta dash as d xi dash d eta dash. And here, because x has been taken as a and y has been taken as b, so in place of xi we write xi naught, and in place of eta we write eta naught. Then we can write xi naught is equal to square root of k by r into a, and eta naught is equal to square root of k by r into b. So now let us evaluate the integral. Now let us evaluate the integral, this one, by separation of variables. And how it is? S xi eta can be written as p xi q eta. S xi eta we write as p xi q eta, and sigma is equal to kappa tau. This is by separation of variables. Now substitute this in equation 23. These values, these ones we substitute and separating the variables. Now let us see, we use this expression 21. So substitute, so by separating the variable, this can be written as kappa p xi. Kappa p xi is equal to I by twice pi power half exponential minus I kr by 2 integral minus xi naught to xi p xi dash exponential I xi dash d xi dash, and tau q eta is equal to I by twice pi power half exponential minus I kr by 2 integral minus eta naught to eta p eta dash exponential I eta dash d eta dash. So these are the two expressions 25 and 26 obtained after separation of variable. This contained both variables together. We have separated the variables of xi and eta. So in terms of xi, the expression is this, and in terms of eta, the expression is this. So 25 and 26 are integrals obtained after separation of variables. Now the integral appearing in equations 25 and 26 are referred to as finite Fourier transforms. They are finite Fourier transforms, and they will tend to normal Fourier transform for xi naught tending to infinity and eta naught tending to infinity. So the limits of integrals will now change from minus xi to plus xi to minus infinity to plus infinity, and from minus eta to plus eta to minus infinity to plus infinity. So what do we have? Kappa p xi is equal to I by twice pi power half exponential minus I kr by 2, or integration from minus infinity to plus infinity p xi dash e exponential I xi dash d xi dash, and tau q eta is equal to I by twice pi power half exponential minus I kr by 2 minus infinity to plus infinity p eta exponential I eta dash d eta dash. So this is 27, 28, and they are normal Fourier transforms now. Now let us assume the solution to be Gaussian. And what type of Gaussian? This is p xi is equal to a exponential minus xi square by alpha square. That is, we assume the solution to be Gaussian. P xi is equal to a exponential minus xi square by alpha square, where alpha is an unknown parameter. Alpha is an unknown parameter. Now substitute equation 29 in 26. That is, p xi is equal to this much. Let us substitute in 27. And use the following equations a and b. Now we have standard integrals. Integral minus infinity to plus infinity minus alpha x square plus ax square plus bx into dx is equal to pi by a power half exponential b square by minus b square by 4a. So we have this minus infinity to plus infinity, this much. We put all these values like this one from here, and then we can get the expression. So what do? Put 29 in 27 and use following standard integrals. And then what do we get? We get this. On the left hand side, kappa exponential minus xi square by alpha square is equal to alpha I by 2 power half exponential minus I kr by 2 exponential minus alpha square xi square by 4. That is 30. If equation 30 is to be valid for all xi, the exponents of left hand side and right hand side must be equal. And if we equate the exponents on both the sides, then alpha is equal to root 2. Then again substitute this value of alpha is equal to root 2 in expression 30, and then what we get? kappa is equal to exponential minus I kr by 2 minus pi by 4. And here I is equal to exponential I pi by 2 has been used. So what do we have? We had the normal Fourier transform. We assume the solution to be Gaussian. We put this solution back in expression 23 and use the standard integral, and we got alpha is equal to root 2. And here alpha was the unknown parameter. So we got the value of alpha is equal to root 2, and then we got kappa. And kappa is equal to exponential minus I k r by 2 minus pi by 4. And here we have used the expression like for I we have used exponential I pi by 2. So if we move in the identical way, that is, we again take a Gaussian solution, this one, like q eta exponential a exponential minus eta square by alpha square, and then we proceed in the similar way, then we can again get that q eta is equal to b exponential minus eta square by 2, and tau is equal to exponential minus I kr by 2 minus pi by 4. So we have got these solutions. So we obtain, we have, of course, hxy is equal to sigma x fxy. We had introduced this one. Fxy was a mode, then hxy was equal to sigma fxy. We had introduced over there, where sigma was a complex constant. And for sigma, we have kappa and we have tau. So fxy can now be written as, from that expression you can see where we had introduced fxy. Now here, so fxy can be written as this taken over here. So fxy is equal to, you can see, sxy exponential I k by twice x square plus y square. You can revert back. Fxy, the function that we had introduced, is equal to, in the plane of the aperture, is equal to sxy exponential I k by twice r x square plus y square. And that is equal to some constant k merged all the constants. K is equal to av, of course, k exponential minus k by twice r x square plus y square, exponential I k by twice r x square plus y square, with k is equal to ab, and sigma is equal to kappa tau, and we have kappa here, we have tau here, and therefore both merge together, so we can write down sigma is equal to this much. Now this expression 30, and this is sigma. Expression 30 gives the transverse distribution of the Gaussian mode of confocal resonator at either mirror. Transverse distribution of Gaussian mode of confocal resonator at either mirror. And we can finally write down hxy is equal to sigma xy is equal to k exponential minus k by twice r x square plus y square exponential I k by twice r x square plus y square exponential minus I k r minus pi by 2. Now, following conclusions may be drawn from expression 37. Number one, if you see mod of sigma is equal to 1, because sigma is equal to exponential minus I something, so mod of sigma is equal to 1. That means the amplitude of the field after 1/2 round trip remains unchanged. The amplitude of the field after 1/2 round trip remains unchanged. Now, this can be attributed to the assumption xi naught tending to infinity, eta naught tending to infinity. Number two, the net phase shift in 1/2 round trip is kr minus pi by 2. Thus, only those frequencies will be allowed for which the phase shift is an integral multiple of pi. That is, kr minus pi by 2 is equal to m pi, where m is equal to 0, 1, 2, 3, etc. From here, k can be written as omega by c. So omega by c r minus pi by 2 is equal to m pi. So if we write omega is equal to twice pi nu, the pi throughout will get cancelled, and we can write down twice nu by c r is equal to m plus half. That means nu m is equal to c by 2 r m plus half. And you can see m is equal to 0, 1, 2, 3, etc. So this expression gives the allowed frequencies of oscillation. These are the only frequencies that are allowed inside the cavity of a confocal resonator system. Different m values expresses different longitudinal modes of the cavity corresponding to Gaussian transverse field distribution. Different m values will give you different modes. Different m values expresses different longitudinal modes of cavity corresponding to Gaussian transverse field distribution. And what is the intermodal separation? Delta m is equal to If you put m is equal to 1 and m is equal to 2 and take the difference, then delta nu m is equal to c upon 2r. So that is the intermodal separation. The Gaussian mode has a curved wavefront of radius of curvature r equal to the radius of curvature of the mirror. You can see it has, if you see the expression 37, then you can conclude that the Gaussian mode has a curved wavefront of radius of curvature r equal to the radius of curvature of the mirror at the mirror. Hence, the Gaussian mode, because you see, the radius of curvature of the Gaussian mode at the surface of the mirror is equal to the radius of curvature of the mirror itself. That means the beam is being incident on the mirror normal to the surface of the mirror. So, and that is why it retraces its path on reflection. So the Gaussian mode has a curved wavefront of radius of curvature r equal to the radius of curvature of the mirror at the mirror. Hence, the Gaussian mode falls normally on the mirror and retraces its path on reflection. Next, 1 by E of the Gaussian field at the mirror can be obtained from equation 37 and may be written as W is equal to 2r by k power half. Next, a Gaussian beam remains Gaussian when it diffracts in a space. That is, due to diffraction, the shape of the beam doesn't change. So a Gaussian beam remains Gaussian when it diffracts in a space. The mode field inside the optical resonator suffers diffraction also. Hence, the mode field remains Gaussian everywhere, both inside and outside the cavity. Next, the Gaussian beam diffracts symmetrically on either side of the waist. The Gaussian beam diffracts symmetrically on either side of the waist. It follows from the symmetry of the resonator that the waist must be at the center of the resonator. You can see from here, the waist must be at the center of the resonator because it has diffraction, identical diffraction on both sides. So therefore, we can say that the Gaussian beam diffracts symmetrically on either side of the waist. It follows from the symmetry of the resonator that the waist must be at the center of the resonator. Now, the change of the beam width of a Gaussian beam as it propagates is given by the formula W square as a function of Z is equal to W naught square 1 plus lambda square Z square by pi square W naught power 4. The waist size W naught at the Gaussian mode, therefore at Z is equal to R by 2. So W at Z is equal to 2R by K power half. That means W naught is equal to R by K power half. The waist size W naught depends on R and lambda. The waist size depends on R and lambda and is independent of transverse dimensions of the mirror. So you can see the figure shows the variation of WZ and the wavefront of the Gaussian mode in a confocal resonator system. You can see from here how it varies as it goes away from the center to any of the mirrors. Symmetrically it varies, and the waist size lies at the center. The 1 by E beam radius of the Gaussian mode at the mirror is 2R by K power half. If the transverse dimension of the mirror is very large compared to 2R by K power half, the mirrors will behave practically as plane mirrors. You see, the 1 by E beam radius of the Gaussian mode at the mirror is 2R by K power half. If the transverse dimension of the mirror is very large compared to this, then the mirrors are going to behave practically as plane mirrors. The transverse dimensions of the mirror is 2A by 2B. Hence, for approximations in equation 25 and 26 to be valid, that we have taken over there, A must be very much greater than lambda naught R by pi, and B must be very much greater than lambda naught R by pi power half. So A must be very much greater than square root of lambda naught R by pi, and B must be very much greater than lambda naught R by pi square root. For example, consider a symmetric confocal resonator system with R is equal to 1 meter and lambda naught is equal to 1 micrometer. For such a case, W naught is equal to 0.4 millimeter. And the beam width at the mirror will be root 2, W naught is equal to 0.7 millimeter. So that is the mode in a confocal resonator system. Thank you very much for your kind attention. So we can see very easily that in the last lecture, we had understood the effect of refraction and reflection inside the cavity resonator. And today we have covered the modes of a confocal resonator system, starting from the expression that we had taken in the last class, that is expression 13 and expression 14 over here you can see. From here we had seen, we had introduced different kinds of functions, converted the variable, then the integral was converted, you can see, to a normal Fourier transform, separation of variables, etc. we are taken, and from that we had taken the solution to be Gaussian. After substituting over here and using the standard integral, we got the unknown parameter alpha is equal to √2. We calculated kappa, we calculated tau, we calculated p as a function of, we found p as a function of xi, q as a function of eta, and then we again reverted back to say that fxy is equal to sxy exponential ik by twice r x square plus y square, and then we found the expression number 37 finally, hxy, because fxy was a mode, so hxy was equal to sigma fxy, where sigma was a complex constant. So from here we made certain conclusions. Mod of sigma 1, that is the amplitude of the field after one round trip remains unchanged, and then we saw what was the mode separation, and then we calculated the waist size also, 1 by e value of the Gaussian field at the mirror we had obtained, that was w is equal to 2k by r power half, and this very expression we used in the small calculation over here to show that the 1 by e beam radius of Gaussian mode at the mirror is 2r by k power half. If the transverse dimension of the beam is very large compared to this one naturally, then the mirrors will behave practically as plane mirrors. The transverse dimension of the mirror is 2 and 2b. Hence, for the approximation that we had taken in 25 and 26 to be valid, and what were they? 25 and 26. What were they? 25 and 26, we had taken this one, that is minus infinity, minus xi naught to plus xi naught, minus eta naught to plus eta naught. So we had taken this one, and then we had converted that to normal Fourier transform. So if we had taken that as the approximation, so for that approximation to be valid, a must be very much greater than square root lambda naught r by pi, and b must be greater than square root lambda naught r by pi. And as an example, we considered a symmetric confocal resonator system with r is equal to 1 meter, lambda naught is equal to 1 micrometer, and for such a case, the waist size came out to be 0.4 millimeter, and the beam width at the mirror was 1 by e of that much, that is square root of 2r by k, and that comes out to be √2. W naught is equal to 0.57 millimeter. And the waist size, you remember, that will be at the center because of the symmetry of the confocal resonator system. So thank you very much for your kind attention. These are certain references you can go with. And this is a disclaimer that this e-content is exclusively meant for academic purposes and for enhancing teaching and learning. Any other use for economic, commercial purpose is strictly prohibited. The users of the content shall not distribute, disseminate, or share it with anyone else, and its use is restricted to advancement of individual knowledge. The information provided in this content is authentic and best as per my knowledge. Thank you very much.